Today I am going to be talking about isotopes and nuclear radiation. So grab your pens, lots of colours, and we're going to mind map out isotopes and nuclear radiation. And you are going to see what an easy peasy subject this is. For isotopes and nuclear radiation, I'm going to draw a bottle of Lucozade because that makes me think of isotopes because it's isotonic. So it's a different thing, but it's a picture, as you know, that makes us think of the word. Now, I'm sure you'll agree that's the worst drawing you've ever seen of a isotonic drink. But that's my drawing. So hopefully you're going to do a drawing that just something around the word isotopes. It could be anything. Could be something around iso, could be something around topes, but anything that's going to just kind of pop the name isotope into your head. So when you see the picture, it makes you think of all the various things that we're going to be talking about with this subject. So I'm now going to picturise nuclear radiation. So again, what makes you think of nuclear radiation? Is it that kind of, well, I'll show you what I'm going to do, which is that kind of nuclear radiation sign. Equally, it could be like a mushroom for like an atomic bomb. Whatever makes you think of nuclear radiation, you draw your picture and I'm going to time-lapse mine. Right, so hopefully you've got some lovely pictures. This needs to be vivid. It needs to speak to your tired mind when you're revising a ton of other GCSE subjects and then you're looking at this one topic and you're trying to get it all in your head as quickly as possible all at once. So for me, I've got my isotonic drink, Lucozade, and I've got my nuclear radiation sign over here. And we're going to draw a first branch up here. And this is going to be labelled isotopes. And well, you've got it from the title actually. Draw isotopes on top of your first branch, and this is where we're going to start. Right, now isotopes, what are they? Think it in your head, please. What are isotopes? Because you know this already from chemistry. Isotopes are, and I hope you've got it in your head, atoms of the same element that have the same number of protons. That's why they're the same element, because an element means it has the same number of protons, the same proton number, but with different numbers of neutrons. Yes? So for example, carbon has two common isotopes, carbon-12, which has 6 neutrons, and carbon-14, which has 8. So the fact that it's called carbon is the element. It means it has the same number of protons. But there are different isotopes of carbon, and each isotope has a different number of neutrons. So let's draw sub-branches. Let's put protons, neutrons, and atomic number, mass number. Protons. These are neutrons. Whilst I'm drawing this, what charge is on a proton, everybody? Do you remember? What charge do protons have on them? Right, atomic number / mass number. I'm going to just abbreviate number there for you. Do you know what charge protons have? Yes, it's +1. What charge do neutrons have? Do you remember from chemistry? Niente, nothing, 0 charge. There's no charge in a neutron. So these add to the mass of a nucleus, but only the protons in the nucleus add to the charge. Yeah, which is always positive because they've got a charge of +1, but that's a side point. Now I'm going to give you an example of some isotopes. So we've got carbon, it's a very standard one. There are two numbers in front of carbon. When you look at the periodic table, there are two numbers. What is this number on the top? Do you remember? Yes, you're correct. Whatever you've said, I'm sure you're correct. Okay, it's the mass number. Yeah, what is the mass number? It's the number of these plus the number of those, because electrons don't have a mass. So we're just counting this one and this one. They've got a mass of 1 each, which is a relative mass. Okay, so carbon has got two common isotopes. One is carbon-12, which has 6 neutrons. Carbon-12 looks like this. The mass number is 12. The mass number is the number of this plus this. The proton number, the atomic number, is 6. That's one isotope of carbon. Another isotope of carbon, I'll write over here. So it's still carbon, it's the same element. A second isotope is carbon-14. Now, because it's carbon, what does it have that's the same as this? What makes it carbon? It's this number, it's the atomic number. Because atoms with the same atomic number are the same element. This is what defines it as the same element, is this atomic number here. But this mass number has changed. So if this mass number is this plus this, the protons are the same, but the neutrons have, but the mass has gone up. It must mean that we have 2 extra neutrons here. So carbon-14 has got 8 neutrons. Yes? This has got 6 neutrons. This one has got 8 neutrons. I'm going to do another one here with our atomic and our mass number, which I probably should have put the other way around, to be fair. Okay, this is oxygen. Every oxygen atom has 8 protons. That means its atomic number down here is 8. Its mass number is 16. That means in this isotope of oxygen, it must have how many neutrons? 8. 8 neutrons here. Yeah? Now, I want to add in something here. So we've spoken about it, but let's put this in. Excuse me. The number of protons defines the element. Yes? So the number of protons defines the element. Let's put a little mini branch. Oh, it looks like it's got a hat on. Okay, try not to make yours look like it's got a hat on. Defines the element. So this is the bit that defines the element. So if it's got 6, the atomic number 6, we know it's always carbon. But what can change is the neutron number. And as you know in chemistry, we're not going to talk about it in physics, but you also know that electrons are the things that react. They're always chopping and changing. They're all over the place. You get ions. You can get positive ions if you've lost an electron. You can get negative ions if you've gained an electron. So electrons can change, and they do regularly. The atomic number defines the element that it actually is. So even if this changes with nuclear radiation, it means that it changes the element. Atoms can have different isotopes, which means that they can exist with different numbers of neutrons. So this is the changeable one, and it can still be called carbon because the protons define the element. I know I have driven this point home, but I want you to really clearly understand this before we move on. so that's really firm in your head. Now, a huge point that I want to make with isotopes, which brings us on to radioactivity, is not all isotopes are stable. Now I'm gonna speed myself up, and I think I'm going to do a horse is stable. I'm so sorry that you missed this, but I messed up my time-lapse video. So you didn't get to see me drawing my incredible horse in its stable. And now you're just going to see me in slow motion colouring it in very badly. I'm really hoping that you have some slightly better art skills, but obviously this isn't an art class. So that's as good as my horse in a stable gets. Not all isotopes are stable. So that's why we're going to talk about radioactive isotopes. So let's do another branch. Let's do a branch called, I think I'm just going to go with my colour scheme here. This branch is going to be called radioactivity. Right, on our radioactivity branch, we're going to put 3 sub-branches. The first one is going to be called alpha. The second one is going to be called, give it a good guess, beta. And the third one is going to be called gamma. Now, radioactivity is the process by which unstable isotopes, so not all stable isotopes are stable, but some of them are. Some of them are very happy, but not all isotopes are stable. That means some are unstable. And radioactivity is the process by which unstable isotopes release energy to become more stable. And there are 3 main types of radiation: alpha, beta, and gamma. I want to picturise this, please. So radioactivity is the process by which unstable isotopes release energy to become more stable. How do you want to picturise that? I'm going to speed up my picture, and you can see what I'm going to do, which I'm not sure what I'm going to draw for this yet, but I'm going to come up with something. I'm also thinking radioactivity, it could be like an old style radio with some activity, like some noise coming out of it, just that you remember the word in relation to what we're doing. But we need in the picture unstable isotopes releasing energy and then becoming more stable. Right, I have gone with a radio, which is unstable because look, it's jittering all over the place. I've got these funky vibrating lines around it. So this is representing, can you see these 2 little knobs here? These are my atoms with their shocked faces because they're unstable. Yeah, and this is jittering around, they're unstable. These are unstable isotopes, which I completely spelled wrong. I have no idea why. Just cover that up with my O. Unstable isotopes, you can label that. Radio, because radioactivity, yes? And this is a definition of radioactivity. It's an unstable isotope which releases energy, which are my zigzaggy lines, to become stable. I have a horse. This is the best horse I've ever drawn. Oh, just give him some eyelashes. So he's just representing that they've become stable. So in here you've got some happy faces. These are two little atom knobs. And then I've put it here as well, so you can see its happy face is become stable. That is the definition of radioactivity that I want you to remember forever. So if you can also picturise it with a radio, that'd be amazing. But just make sure that however you do it, you've got some unstable isotopes on this side, you've got them releasing energy, and then you've got them becoming stable, however you want to picturise that over here. Right, now we're going to move on to our 3 types of radiation. We're going to talk about alpha radiation. So alpha radiation is exactly the same as a helium nucleus. So if you look at the periodic table and helium has 2 protons and it also has 2 neutrons. So I'm just going to do this. I'm going to write my protons as red because I give positive charged things red. And my neutrons, I'm going to colour them green because they're neutral. So you can do it differently if you like, but I just want to show you that an alpha particle is like a helium nucleus. It's got 2 protons and it's got 2 neutrons. So you draw your own alpha particle. And there are a few things we need to remember about this. Alpha particles are strongly ionizing. What does this mean? So let's come back to, well, chemistry, but also we've done a little bit in physics as well, but very much we need to know about ions in GCSE chemistry. What does ionizing mean? Think about it in your heads. What does that mean? What happens when you ionize something? So alpha particles are strongly ionizing. Now, you'll know from chemistry, ions can be formed by the gain or loss of electrons, because you can create cations and you can create anions. Cations, if you lose an electron, which is what alpha particles cause, they ionize in that direction. But ionizing also takes place when an atom gains an electron, and you will get a negatively charged ion, which is called an anion. It makes charged particles called ions that have got a positive or a negative charge. Now, in physics and with radioactivity and alpha particles, they only cause atoms to lose electrons. So we're not talking about creating negative ions here when they gain electrons. We're only talking about knocking electrons out of atoms and causing positive ions. Why? Why does it do that? Why does it cause atoms to lose electrons and form positive ions? If you think about what an alpha particle is, it's a helium nucleus consisting of 2 protons and 2 neutrons. What charge do the protons have? They've both got a charge of +1. What charge do the neutrons have? Nothing. Neutrons don't have a charge. So this particular particle carries a 2+ charge, which I'm actually going to write in so that you remember, 2+. It's also got a huge mass. We're not talking about electrons here. With all of these 4 particles, subatomic particles, have a mass, don't they? A relative mass of 1. So it's got a large mass and a high charge of +2. And this makes it really effective at interacting with nearby electrons. So as this alpha particle moves through a material, it attracts negatively charged electrons from the outer shells due to its positive charge, yeah? The electrons are pulled away from the atoms, leaving the atoms as positively charged ions, which is why this process is strongly ionizing, because it creates positively charged ions. Yeah. Now, even though this is strongly ionizing, alpha particles can be stopped pretty easily. The only thing you need to stop an alpha particle, alpha radiation, is a sheet of paper or even your skin, your hand. So it's stopped pretty quickly. So it's really strongly ionizing, but you can stop these very quickly. So you can either draw here a sheet of paper. Oops, sorry. Sheet of paper, which is fine, apart from sheets of paper are kind of difficult to picturise. Or if you like, you can put a hand coming out of my paper, how strange, but they can be stopped by a sheet of paper or even skin. So they can be stopped pretty easily. Beta radiation, if we move down here, is the release of a high-speed electron from the nucleus when a neutron turns into a proton. Let me say that again. When a neutron turns into a proton, it releases a high-speed electron. So Right, I had to pause there for a second to figure out how I could represent high speed. And as you can see, I've done a terrible job of it. But this is a high-speed train. I'm really confident that you can come up with a better picture for high speed. But there we go. And I'm just going to make this a neutron. So this one is green. And it's turning into an electron. Turning into a proton. Which, if you like, instead of doing like this, these edges, you could give it a positive charge, if you like. Neutrons haven't got a charge. They're neutral. So if a neutron's turning into a positive charge, it deposits the negative charge, which is your high-speed electron, which I'm still going to do as little dementors, even though that looks nothing like a dementor. This is my electron, and he's travelling at high speed. So this is your beta particle, your high-speed electron that's released when a neutron turns into a proton. Yeah, that's what a beta particle is. Now, this is moderately ionizing. So alpha's strongly ionizing. Look, it's got a 2+ charge. So it massively attracts your electrons and kicks them out. Beta is moderately ionizing. And it can be stopped by thin sheets of aluminium. So it can't be stopped by a sheet of paper or your skin, but it can be stopped by a thin sheet of aluminium. So if you have a silver pen, oh, do I have a silver pen? I do. So this guy is stopped by my thin sheet, coloured in my silver pen, of aluminium. So let's put Al, if you remember from chemistry, is your aluminium. And this sheet is fairly thin. If you've got a better way of doing thin, you could put a skinny person on there, or a skinny Al, or any other way you can think of. And this stops it. So we can put a little cross maybe for the stopping purposes. Okay, just to say that that's how you stop them. Yeah, so your alpha's got your 2+ charge, it's got your 2 protons, 2 neutrons, strongly ionizing, which I spoke through, but it can be stopped by a sheet of paper or even your skin. Beta, when a neutron turns into a proton, it emits from the nucleus, because this is where neutrons and protons are, a high-speed electron, which is called a beta particle. It's moderately ionizing, and it can be stopped by a sheet of aluminium. The last one we have is gamma radiation, which you've probably heard of. Gamma radiation, if you've already done my EM spectrum, is an electromagnetic wave. So hang on a sec. It's an electro or an EM wave. It's on the electromagnetic spectrum. Up the very top, if you remember, it's got high frequency and it transfers a lot of energy. So, and it's a transverse wave. All electromagnetic waves are transverse waves. So I'm going to do a wave like this because it's got a high frequency and a short wavelength. Transfers a lot of energy, does gamma. Now, it's weakly ionizing. So actually, good point. Should we give this a strong arm? Alpha, should we give it a nice big muscle? Okay, that's not a hugely big muscle. Gamma is weakly ionizing, so it's got quite a thin arm, to be honest. Oh gosh, that looks like a foot, but never mind. Strongly, weakly, moderately. Mine's pink. Weakly ionizing. But it's very, very, very penetrating. Only thick lead or concrete can stop it. So not sure how you want to picturise lead. You might want to do, I would do a pencil, but because I've got lead in it, but that's not very thick. If you want, you could just do a huge block of concrete, 5 metre wide. Very penetrating. Penetrating. So you can picturise penetrating as well if you like. So it can only be stopped with concrete, huge, massive 5 metres of it, or lead. It can be stopped by lead. Now, let's move on. We're going to go on to half-life. I haven't used red. Should have sped that up for you, but never mind. Half-life. From half-life, we're going to draw 2 branches. One's going to be the definition, what is half-life? And the other will be we'll talk about the applications of half-life as well, because it can be used. Half-life is the time it takes for half of the radioactive nuclei in a sample to decay. So I'll say that again. The time it takes for half of the radioactive nuclei in a sample to decay. So it's a measure of how quickly a radioactive substance loses its activity. Yes? The radioactivity being this. So how can we picturise this? The time it takes, let's go with a clock. I'm going to go with a big fat half. And decay, oh, this could be nasty. What should we, so half of a substance to decay. Not going to lie, when I think of decay, I think of like skeletons. So here's my decaying human. With all its teeth. Oh my lord, what is this? Okay, I think I've missed something here. There must be something, some other way of drawing a skeleton. I'm sure you can draw a much better skeleton than this. So this is me just saying that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is our clock, so it's the time. It takes for half, that's fairly self-explanatory, of the radioactive nuclei in a sample to decay. I'm going to put radioactive in here. Half time for or how quickly a radioactive substance loses its activity. Let's put a couple of real life examples for you. So half-life can be used in carbon dating, if you've heard of that. So carbon dating determines the age of ancient objects. So we could put an ancient object. What should we put? Ancient object. Maybe like an old coin. Would have to have a profile face on it. P. Okay, that's my ancient object. Please come up with something better. That is terrible. So carbon dating can be used to determine the age of ancient objects, and medical traces can be used for diagnosing diseases. So you can also have, you can use the half-life for, well, as a medical tracer. And that's for diagnosing diseases. Okay. Now, apart from my terrible coin, I seem to not really have too many pictures on this side, but please feel free. Oh, look, I've got a gold pen. Oops. Please feel free to colour your... Oops. Okay, it's probably better, to be fair, than what I had on there before. That's my ancient coin. Medical tracer. Maybe you can have a stethoscope. Okay, so we think of medical stethoscope for diagnosing diseases. So medical tracer for diagnosing diseases. Right, last one, nearly there. Do not worry. I'm going to go pink. The last thing we're going to talk about is nuclear fission and fusion. So nuclear physics, we also study fission and fusion. Fission is the splitting of a heavy nucleus into smaller ones, which releases energy. That's what's used in nuclear reactors. So if you heard of nuclear reactors creating energy, electricity, and so forth, that's the basis of it, fission, splitting heavy nucleus into smaller ones, which releases energy. Fusion involves the joining of two light nuclei to form a heavier one, which releases even more energy. And that's what happens in stars like our sunshine. Fusion takes place. Two light nuclei form a heavier one, and that releases loads and loads of energy. So let's just quickly make a note of that. We've got fusion and we've got fission. Nuclear fission and fusion. Now, fission is the splitting of a heavy nucleus into smaller ones. So how can we picturise heavy? I guess we can have a big nucleus here. Into smaller ones. And as it does so, it releases energy, which, energy. It's going that way, it's releasing it. So it's heavy. You might want to put a scale or like a weight. So heavy nucleus into smaller ones. We'll put the word split. That's what fission is. And you could probably do a much better job than me, but I'm going to write here nuclear reactors. Nuclear reactors, because they release energy and we can harvest that and we can power our homes with it. So that's the basis of nuclear reactors. I might do a building with some chimneys. That's my nuclear reactor. On the other hand, we've got fusion, which is the fusion of two light nuclei to form a heavier one. So it's basically the reverse. So you've got two light nuclei. Circle around the edge, by the way, it's just my outer energy field. I'll put a little arrow perhaps. So they come together to form a heavier one. And this releases tons and tons of energy. And that happens in stars, like our sunshine.